On the 3rd of September 1939, Prime Minister Neville Chamberlain addressed the House of Commons with words that would reshape British industry overnight. Britain was at war with Germany. The Royal Air Force possessed 1,750 frontline aircraft. The Luftwaffe fielded 4,161. But the numerical disadvantage was only the beginning of Britain's aviation crisis. Behind those numbers lay a dependency so complete, so absolute, that it threatened to ground the RAF before a single sortie could be flown. Every spark plug in every British aero engine came from Germany. The mathematics were brutal. The Air Ministry calculated immediate requirements at 2 million spark plugs for existing engines, with projected wartime demand reaching 8 million within 18 months. Current British manufacturing capacity, 0 plugs per day, meeting aviation specifications. The entire global market for aviation spark plugs was dominated by a single company, Bosch of Stuttgart, holder of critical patents developed over 3 decades of refinement. Their ceramic insulators withstood combustion temperatures exceeding 2,000 degrees Fahrenheit, whilst maintaining electrical resistance under extreme vibration and pressure cycling. British manufacturers produced adequate spark plugs for motorcars and lorries, but aviation demanded precision an order of magnitude beyond automotive standards. The technical requirements revealed the depth of the problem. An aero-engine spark plug operated in conditions that would destroy automotive components within minutes. Temperature cycling from -40 degrees Fahrenheit at altitude to 2,000 degrees in the combustion chamber occurred every few seconds during combat maneuvers. Pressure differentials from 14 pounds per square inch at sea level to 4 pounds at 20,000 feet created stress on the ceramic insulator that required perfect material density to prevent cracking. Vibration frequencies in the 2,000 to 4,000 cycles per minute range from the engine transmitted directly through the plug body. Electrical potential of 25,000 volts across an air gap, measured in thousandths of an inch, repeated 15 times per second in each cylinder. A single microscopic crack in the ceramic allowed electrical tracking that caused misfiring. A gap tolerance error of 2,000ths of an inch changed ignition timing enough to reduce engine power by 15%. The electrode material had to resist erosion from 2,000-degree combustion whilst maintaining precise geometry for 50 hours of operation. Bosch had spent 30 years solving these problems. Their engineers in Stuttgart had developed ceramic formulations, electrode alloys, and manufacturing processes that represented the accumulated knowledge of hundreds of specialists working across multiple disciplines. The critical patents covered not just the final plug design, but the production methods. Kiln temperature profiles for ceramic firing, electrode grinding specifications, assembly torque requirements, quality inspection procedures. Britain had 6 months before existing stocks ran out. Building an aviation spark plug industry from nothing in that time frame appeared impossible. The problem revealed itself in layers. War declaration severed supply instantly. Bosch couldn't deliver to an enemy nation even if neutral intermediaries offered to facilitate shipment. Their patents covered the critical ceramic formulation, the electrode geometry, the gasket design, the heat range specifications. Champion Spark Plug Company in America produced aviation plugs under Bosch license, but U-boats made Atlantic shipping increasingly uncertain. Large Plugs Limited in Rugby manufactured excellent automotive plugs, but had never attempted aviation certification. The Air Ministry faced an impossible situation. Expand the RAF from 1,750 aircraft to a planned 12,000 by 1941, equip each aircraft with engines requiring between 8 and 24 spark plugs, depending on configuration, replace plugs at intervals of 50 flying hours under combat conditions, and accomplish this transformation whilst the only proven supplier operated factories in enemy territory. The solution to Britain's crisis had been living in Birmingham since 1903. though the man who created it never lived to see his innovation prove essential to national survival. Albert Frederick Lodge was born in Stourbridge in 1854, the son of a master craftsman in the glass industry that dominated the region's economy. The Midlands in the 1850s were transforming from agricultural communities into industrial centres, and Stourbridge specialised in high-quality glass-making that supplied everything from bottles to optical lenses. Young Albert grew up surrounded by precision craftwork and the understanding that microscopic tolerances separated acceptable products from failures. His first career took him away from glass entirely. The bicycle craze of the 1870s offered opportunities for young men with mechanical aptitude and competitive spirit. Lodge raced throughout the Midland circuit, competing in events from Birmingham to Nottingham. He showed promise but never dominated, finishing in the top 10 consistently without achieving victories that might have supported him as a professional cyclist. The crash during the 1878 season at a race in Leicester ended those ambitions permanently. He struck another rider during a sprint finish, went over the handlebars, and landed on cobblestones with his left shoulder taking the full impact. The collarbone shattered in 3 places. Victorian medicine could set the bone, but couldn't restore the precise alignment required for the shoulder mechanics that cycling demanded. After 6 months of attempted recovery, Lodge accepted that his racing career was finished. He was 24 years old, trained for nothing but cycling, and needed to find a new direction. If he couldn't race, Lodge later wrote in correspondence preserved at the British Motor Industry Heritage Trust, perhaps he could improve the machines. He apprenticed with John Marston's carriage-making firm in Wolverhampton, learning metalwork and precision assembly through the traditional guild system that required 3 years of training before achieving journeyman status. Carriages in the 1880s were precision products requiring expert craftsmanship in woodwork, metalwork, upholstery, and final assembly. Lodge focused on the metal components: axles, springs, bearings, and the increasingly sophisticated braking systems that customers demanded as carriages became faster and heavier. The precision mindset from his racing days translated directly to manufacturing tolerances. A bearing race machined to the wrong tolerance would cause premature wear. A spring tempered incorrectly would fail under load. Lodge developed an obsession with getting the details exactly right. He established his own workshop in 1885, manufacturing bicycle components for the growing market of recreational cyclists who couldn't afford complete machines from major manufacturers but could build their own from quality parts. Lodge produced hubs, pedals, chains, and sprockets machined to tolerances that exceeded industry standards of the era. His business remained small, employing 5 workers and producing several hundred components per month, but it earned a reputation for reliability amongst Midlands cyclists who valued durability over fashion. The internal combustion engine arrived in Britain through imports and licensing arrangements in the 1890s, transforming from laboratory curiosities to practical motor cars and motorcycles by the turn of the century. Lodge noticed that these early vehicles experienced frequent ignition failures that left riders stranded. The spark plugs of the era used mica insulation that deteriorated under heat and moisture. Mica was cheap and readily available, but it absorbed water from humidity and delaminated under thermal cycling. A plug might work perfectly when installed, then fail after 50 miles of operation when moisture penetrated the insulator. Lodge obtained samples of failed plugs from frustrated motorcyclists, dissected them in his workshop, and began experimenting with alternative materials. The breakthrough came from his family background in glassmaking. Lodge understood that ceramic materials could be formulated and fired to achieve specific properties. Standard pottery absorbed moisture, but porcelain fired at higher temperatures achieved density that made it nearly waterproof. The challenge was manufacturing complexity. Mica insulators were stamped from sheet material in simple dies. Porcelain required mixing specific clay formulations, molding to precise dimensions, whilst accounting for shrinkage during firing, then heating in kilns to temperatures exceeding 1,400 degrees Celsius for specific time profiles that produced the correct crystal structure. Too low a temperature, and the porcelain remained porous. Too high and thermal stress created microcracks. The firing cycle had to ramp up gradually, hold at peak temperature for hours, then cool slowly to prevent stress fractures. By 1902, Lodge had developed a spark plug using porcelain insulation that maintained electrical resistance under heat and vibration that would destroy mica within hours. The porcelain used alumina content higher than standard ceramics, achieving density that prevented electrical tracking under stress. He patented his design in 1903, British patent 10,663, covering improvements in sparking plugs for internal combustion engines, and founded Lodge Plugs Limited in Rugby that same year with initial capital of £2,000 raised from local investors who recognized the growing motor car market. The Rugby location was chosen for its central position in Britain's emerging automotive industry, with access to rail connections and a skilled workforce from the town's established engineering trades. The technical breakthrough lay not just in the ceramic material, but in the complete assembly system. The electrode had to be positioned within the porcelain insulator with precision of plus or minus 0.005 of an inch, held in place by a copper core that conducted heat away from the electrode whilst maintaining electrical insulation from the steel shell. The gasket compressed to exact specifications to create a gas-tight seal whilst allowing thermal expansion and contraction through hundreds of heating cycles. The steel shell threads had to match engine specifications precisely so the plug would seat at the correct depth in the combustion chamber without bottoming out or sitting too high. 17 distinct operations were required from raw materials to finished product, with quality inspection at each stage. Workers needed months of training to achieve the precision that Lodge demanded, learning to recognize the subtle visual indicators that distinguished acceptable ceramics from those with microscopic flaws that would cause field failures. Lodge plugs gained commercial recognition throughout the Edwardian era and into the 1920s as motorcars transitioned from luxury novelties to practical transportation. The company supplied spark plugs for Rolls-Royce motorcars, establishing a relationship that would prove crucial 2 decades later, when Rolls-Royce began developing the Merlin Aero engine. Bentley racing automobiles used Lodge plugs in their victories at Le Mans in 1924, 1927, 1928, 1929, and 1930, with race mechanics noting that plug reliability under 24 hours of continuous high-speed operation exceeded any competitor. Norton Motorcycles specified Lodge plugs as original equipment, and the racing successes accumulated endorsements that drove commercial sales. Malcolm Campbell used Lodge plugs in Bluebird when he set the land speed record at 301 miles per hour at Bonneville Salt Flats in 1935, specifically requesting Lodge products because he trusted them not to fail at sustained full throttle. Amy Johnson flew with Lodge plugs installed in her Gypsy Moth during her solo flight to Australia in 1930, 19 days of flying across hostile terrain where a single engine failure meant death. She praised the plugs publicly upon her return, noting they had never caused a moment's concern throughout the journey. But the business relationship between Albert Lodge and the company bearing his name had deteriorated through the 1920s. Lodge himself didn't own controlling interest in Lodge Plugs Limited. The original investors who provided capital in 1903 held majority shares, and as the company grew profitable through the automotive boom, disagreements emerged over expansion strategy and product development. Lodge wanted to invest heavily in aviation applications, recognizing that aero engines represented the most demanding environment for spark plugs, and that dominance in aviation would establish technical credibility across all markets. The board of directors preferred to focus on the far larger automotive market, where sales volumes and profit margins seemed more certain. Lodge argued that Bosch was already establishing dominance in aviation through their relationship with German aero engine manufacturers, and that lodge plugs needed to compete for military contracts before the technical gap became insurmountable. The board saw military work as low-profit distraction from the thriving civilian market. The conflict reached crisis in 1927 when Lodge threatened to resign rather than accept the board's decision to decline an Air Ministry request for proposal on spark plugs for the new generation of aircraft engines being developed for the RAF expansion program. The board chairman, Sir William Morris, later Lord Nuffield, argued that the requested specifications couldn't be met profitably at the Air Ministry's proposed pricing. Lodge countered that losing the contract meant ceding aviation leadership to Bosch permanently. The board voted to decline the contract. Lodge resigned immediately. Legal restrictions in the company charter prevented him from founding a competing spark plug company in Britain or soliciting Lodge Plug's employees for 5 years after separation. At age 73, the inventor who created the modern porcelain spark plug found himself legally prohibited from working in the industry he had founded. He spent the remaining decade of his life consulting on ceramic engineering projects for the pottery industry in Stoke-on-Trent, work that paid modestly but bore no relation to the innovation that had defined his career. Albert Lodge died on the 15th of March 1937, aged 83. Never knowing that his resignation over aviation spark plugs would prove to have been the correct strategic position, or that his innovation would prove essential to British survival in a war he didn't live to see begin. The Air Ministry turned to Lodge Plugs Limited in September 1939, with requirements that seemed impossible to everyone except the company's engineering director, who had worked under Albert Lodge in the 1920s and understood both the technical capability and the production challenges. The Rolls-Royce Merlin engine powering the Hurricane and Spitfire used 24 spark plugs per engine, 2 per cylinder for redundancy, in case one plug failed during combat. The Bristol Hercules Radial used 18 plugs. Current RAF aircraft required 84,000 plugs immediately for existing engines, with replacement demand of 168,000 plugs per month, assuming 50-hour service intervals under combat conditions that caused accelerated wear. The planned expansion to 12,000 aircraft by 1941 would require 2.8 million plugs in inventory, with monthly consumption exceeding 500,000 plugs once the expansion was complete. Lodge's Rugby facility was producing 200 aviation specification plugs per day in September 1939. All for civilian racing and sport aviation, where demand was trivial compared to military requirements. The company's engineers told the Air Ministry they could scale to meet demand. The Air Ministry officials were skeptical but had no alternatives. The transformation began in October 1939 with an expansion program that consumed every available resource the company could allocate. Lodge Plugs hired 300 workers in 4 weeks, doubling the workforce from 280 to 580 employees. They leased adjacent factory space in Rugby previously used for textile manufacturing and installed ceramic kilns operating continuously on 3 shifts. The kilns alone represented major capital investment, each costing £8,000 and requiring 6 weeks from order to installation to commissioning. The supply chain for raw materials became a logistical battle fought across Britain through the Ministry of Supply allocation system. Alumina came from China clay deposits in Cornwall, shipped by rail in 50-pound bags that required careful handling to prevent moisture contamination. Copper came from mines in Wales, with supply increasingly constrained as copper was diverted to electrical wiring for aircraft and ammunition cartridge cases. Maker for gaskets came from India via convoy, with Atlantic U-boats making every shipment uncertain. Tool steel for electrode manufacture came from Sheffield, where every steelmaker was overwhelmed with orders for aircraft components, armor plate, and gun barrels. The production numbers told the story of industrial transformation under impossible pressure. December 1939, production reached 1,200 plugs per day. January 1940 showed 2,800 per day. March hit 5,400, June exceeded 8,000. Each month required hiring more workers, installing more equipment, securing more raw materials through a procurement system that prioritized everything as essential. The factory operated 3 8-hour shifts with workers cycling through stations to maintain precision whilst combating fatigue. Training new workers became a continuous process. Women with no manufacturing experience learned ceramic inspection by examining hundreds of samples under magnification until they could recognize the hairline cracks or density variations that predicted field failures. Men learned precision grinding on electrode tips, working to tolerances measured in 10,000ths of an inch, whilst operating machines that could easily grind the electrode too far with one moment of inattention. Assembly workers learned torque specifications for tightening the plug assembly, where too little torque allowed gas leaks and too much torque cracked the ceramic. Dorothy Blackwell, aged 19, began work at Lodge in November 1939, assembling electrode cores. She had worked previously at a hosiery factory in Coventry, before being recruited to munitions work through Ministry of Labour campaigns, encouraging women to support war production. "The foreman told us these plugs would keep hurricane pilots alive," she recalled in a 1994 interview preserved in the Imperial War Museum Oral History Collection. "Every plug I touched, I thought about a pilot depending on it working at 20,000 feet. I'd never seen an aeroplane up close, didn't know anything about engines, but I understood that if I made a mistake, someone could die." We all felt that. The woman working next to me lost her brother at Dunkirk. She assembled plugs like she was fighting the war herself, which she was. Working conditions were brutal throughout 1940 and into 1941 as production demands escalated. The ceramic kilns raised workshop temperatures to 95 degrees Fahrenheit, even in winter, with heat radiating from the brick structures that operated continuously. Summer heat reached 110 degrees, turning the factory floor into an environment that caused workers to drink gallons of water per shift just to avoid heat exhaustion. Workers handling hot ceramic wore heavy gloves that made fine assembly work difficult, requiring them to develop techniques for feeling component alignment through thick fabric. The precision grinding operations produced metal dust that coated everything: floors, equipment, workers' clothing, creating a grey patina that required constant cleaning to prevent the dust from contaminating ceramic surfaces. Women comprised 67% of the workforce by 1941, taking positions in assembly and inspection, whilst men operated the heavier machinery and managed kiln operations. Shifts ran 7 days per week, with only Christmas and Easter granted as holidays. The Ministry of Labour regulations technically limited women's working hours, but Lodge plugs received exemptions based on essential war production status. Weekly production in July 1940 reached 56,000 plugs, distributed to RAF squadrons desperately burning through their stocks of surviving Bosch plugs as combat intensity increased. August showed 67,000 plugs per week. September hit 73,000 as the Battle of Britain reached its peak intensity, with Fighter Command sometimes consuming 15,000 plugs per week to keep Hurricanes and Spitfires operational. Every plug shipped from Rugby carried an inspector's stamp certifying it had passed all quality checks, a level of traceability unprecedented in British manufacturing, but essential when component failure meant pilot death. The Air Ministry demanded proof that Lodge plugs met Bosch standards before accepting them for widespread service. They designed a qualification test intended to destroy inferior products. Each plug was subjected to 150 hours of continuous operation in a test engine cycling between idle and full throttle every 30 seconds. Temperature extremes ranged from 150 degrees Fahrenheit at idle to 2,100 degrees at full power. Vibration frequencies matched combat conditions. Pressure cycling simulated altitude changes from sea level to 30,000 feet. Champion plugs from America failed at an average of 89 hours with ceramic cracking. C-plugs from General Motors failed at 107 hours with electrode erosion. Lodge plugs completed the full 150-hour test with no failures. 3 samples were continued to 200 hours as an extreme stress test. All 3 remained functional when the test was terminated. The results weren't close. The Air Ministry awarded Lodge Plugs Limited a contract in June 1940 for 2.5 million plugs at 7 shillings 6pence per plug, with delivery schedules requiring 500,000 plugs by September 1940, 1 million by December 1940, and the remainder by March 1941. The total contract value exceeded £900,000, equivalent to £60 million in 2025 purchasing power. Every Hurricane and Spitfire squadron received priority allocation of Lodge plugs, with installation beginning in July 1940 as the Luftwaffe prepared for the invasion of Britain. Flight Lieutenant Geoffrey Wellham of 92 Squadron flew Spitfires equipped with Lodge plugs throughout the Battle of Britain from his base at Biggin Hill. His logbook, preserved at the RAF Museum Hendon, records 53 combat sorties between August and October 1940, each entry noting engine performance and any mechanical issues encountered. On the 15th of September 1940, the day that would later be designated Battle of Britain Day for the intensity of Luftwaffe attacks on London, Wellham engaged a formation of Heinkel 111 bombers over Kent in combat that tested every component of his aircraft. Climbed to Angels 2-2, engaged from astern. His combat report noted, all guns firing, Merlin running smooth at full boost plus 9 pounds emergency power. Temperature normal throughout engagement. No engine trouble whatsoever. The phrase, no engine trouble, appeared consistently in combat reports from squadrons equipped with Lodge plugs, a contrast to earlier reports from July and August, when aging Bosch plugs were failing under combat stress and causing forced landings that sometimes proved fatal if they occurred over the Channel or enemy territory. Maintenance logs from 92 Squadron show that Spitfires equipped with Lodge plugs maintained operational readiness rates of 87% during September 1940, compared to 64% for aircraft still using surviving stocks of Bosch plugs experiencing deterioration from extended service life beyond their designed 50-hour replacement intervals. The difference of 23 percentage points translated directly to combat effectiveness. More aircraft available meant more pilots in the air to intercept raids. 0 combat losses were attributed to spark plug failure during the Battle of Britain amongst aircraft equipped with Lodge products. Several pilots survived forced landings due to battle damage specifically because their engines continued running on Lodge plugs, despite damaged fuel systems or cooling systems that would have caused misfiring with inferior ignition components. Squadron leader Brian Lane of 19 Squadron returned to base on the 24th of August, with 6 feet of his Spitfire's starboard wing destroyed by cannon fire, maintaining level flight only because his Merlin engine continued developing power smoothly on the remaining plugs after several were damaged by the same cannon shells that tore apart his wing structure. The Luftwaffe captured intact examples of Lodge spark plugs from crashed British aircraft in September 1940. German technical intelligence reports, translated and published in the British Intelligence Objectives Subcommittee Assessments of 1945, acknowledged that the British ceramic insulator demonstrates superior resistance to thermal shock compared to current Bosch production samples. The analysis noted electrode geometry modifications that improved heat dissipation. But German manufacturing facilities lacked the capacity to respond. Bosch factories in Stuttgart had been designated for dispersal to protect them from strategic bombing, with production distributed to smaller facilities across southern Germany. The ceramics production required kiln temperatures and quality control that the dispersed facilities struggled to maintain. Skilled workers had been conscripted for military service. Raw material allocations prioritized other weapons systems. The window for catching up with British spark plug technology had closed before German engineers fully understood the gap. RAF Bomber Command launched Operation Abigail on the night of the 8th of September 1940, targeting the Robert Bosch electrical works in Stuttgart Feuerbach. 73 Wellingtons and Hamptons dropped 120 tons of high explosive and incendiary bombs. Post-raid reconnaissance showed severe damage to 3 production halls and the main administrative building. 47 workers died. Production ceased for 3 weeks whilst debris was cleared and equipment relocated. Similar raids followed in October and November, each temporarily disrupting Bosch spark plug production. But stockpiles accumulated before the war, imports from occupied territories, and substitution from automotive production prevented German aero engine programs from experiencing critical shortages. The irony was evident to RAF planners even at the time. Whilst Bomber Command crews risked their lives attempting to destroy German spark plug factories, Britain was producing superior alternatives in unlimited quantities from facilities in Rugby that never experienced a single Luftwaffe raid. The strategic reversal became complete by 1942. Lodge Plugs Limited expanded to 4 factories, employing 3,200 workers, producing 2.3 million aviation spark plugs annually. The company supplied not only the RAF, but also the US 8th Air Force, operating from British bases, Commonwealth Air Forces, and the Soviet Union through Lend-Lease allocations. Post-war production transitioned to civilian aviation and automotive markets. The company established international manufacturing subsidiaries in Australia, Canada, and South Africa. By 1960, Lodge Plugs held 34% of the global aviation spark plug market. The technology developed under wartime pressure became standard for all high-performance engines. Modern aviation spark plugs use ceramic formulations descended directly from Lodge's wartime innovations, with alumina content specifications and firing temperatures matching those developed in Rugby between 1939 and 1941. Albert Lodge never witnessed the vindication of his life's work. He died 2 years before the war that would prove his ceramic insulator design essential to British survival. Lodge Plugs Limited continued operating under that name until 1989, when it was acquired by Cooper Industries and merged into Champion Aerospace. The Rugby factory that produced 8,000 spark plugs per day during the Battle of Britain closed in 2007. Its production transferred to facilities in Mexico and China. But the fundamental innovation remained. Porcelain insulation fired at extreme temperature to achieve density that resists thermal shock and electrical tracking. Every spark plug in every aircraft flying today uses technology that can be traced to a bicycle racer from Stourbridge who noticed that mica insulators failed under heat. The historical irony extends beyond technology to national industrial capability. Germany dominated global spark plug production in 1939, with Bosch controlling 60% of world output through patents, manufacturing expertise, and 3 decades of refinement. Britain possessed no aviation spark plug industry when war began. 4 years later, Britain was exporting superior spark plugs to allies, whilst German factories struggled to maintain quality under bombing and resource constraints. The nation that invented the modern internal combustion engine and developed the automotive spark plug to its highest pre-war refinement found itself surpassed by a competitor that started from 0 capacity when conflict began. The mathematics of industrial transformation remains striking. Lodge Plugs increased daily production from 200 units in September 1939 to 8,200 units in September 1940, a 41-fold increase accomplished in 12 months whilst maintaining quality standards that exceeded pre-war German benchmarks. The company hired and trained 2,900 workers, 2/3 of them women with no previous manufacturing experience, and achieved defect rates below 0.3% in final inspection. Total wartime production exceeded 9 million spark plugs, everyone manufactured to specifications that required 17 distinct operations and quality verification at each stage. Not a single RAF aircraft was lost to spark plug failure throughout the war. Dorothy Blackwell worked at Lodge Plugs until 1946, when post-war demobilization reduced the workforce. She married, raised 3 children, and lived in Rugby until her death in 2003. Her wartime production records show she personally assembled 847,000 spark plug electrode cores between November 1939 and May 1946. At 50-hour replacement intervals under combat conditions, those plugs provided 42.3 million engine hours of reliable ignition. She never flew in an aircraft and never met a pilot whose life her work protected. But the connection existed nonetheless, written in ceramic and copper and porcelain, fired to 1,400 degrees Celsius. Every hurricane that climbed to intercept raiders over Kent, every Spitfire that engaged Messerschmitts over the Channel, every Lancaster that reached Berlin and returned, all of them depended on components manufactured in Rugby by workers who understood that precision wasn't merely a production requirement, but a moral obligation to pilots who trusted their lives to engineering they would never see. The dependency that threatened Britain in September 1939 reversed completely by 1945. Bosch resumed civilian production after the war, rebuilt its facilities, and regained market share in automotive applications. But in aviation, German engineering came in second place. The spark plugs that powered Allied victory were British, manufactured in a factory town in Warwickshire by workers who had never built aircraft components before war demanded it. Albert Lodge's innovation, developed to solve the ignition problems of Edwardian motorcars, proved essential to the survival of a nation he never lived to see endangered. The mathematician who calculated British requirements at 2 million plugs in September 1939 would have considered that target impossible. The factory that delivered 9 million plugs by 1945 proved otherwise. The impossible mathematics became simple arithmetic when national survival depended on the answer.